Hey everyone, so welcome to a walkthrough for homework 2, questions 2 through 4. For question 1, that is in another video, so just check it out in this playlist. Great, so let's start with homework question number 2. It says there is a thin layer of liquid and it's draining from an inclined plane, and it has a velocity profile that we're given right here. Great, and then we know V0 is the surface velocity. And if the plane has width W into the paper, let's write that right there, determine the volume rate of flow in the film. So that's one thing we need to determine. Second thing we need to determine, estimate V0. So that's number 2. And then based on the known parameter, the film height H, which is right here, H, and then we have flow rate Q. Great, so it wants us to find Q first, and then basically estimate V0 using Q. So let's get started with what we do know. We do know the velocity profile, Vx, right? And it's in terms of y is equal to V0 2y over h minus y squared over h squared, sorry. So we do know this, and now we need to solve for Q. So if we remember Q, the expression for Q is the volumetric flow rate. And that is going to be the integral of the velocity, right? In this case, Vx. And then it's going to be over the cross-sectional area of flow, and dA. Right, so we know these two things. So all you do here is plug and solve for Q. So you're going to plug in Vx. Right before we do that, one thing to note is first, what is the cross-sectional area? If we take a look right here, we know that first it's going to flow basically on a width of W and some height H, right? And as you can tell from the velocity profile, this actually is changing. The velocity profile based on our y direction, which we can also see right here, y is going to be changing. So this is going to be changing dy from a height of 0 to h. So by now you should be kind of familiar. The width does not, the velocity profile does not change by the width, right? So that's locked in. So we can rewrite this essentially as QV equals, first we have the cross-sectional area from 0 to h, Vx, then we have times dy times width. And we can actually pull this width value out of this expression to make our life easier. Great, so it's going to be width times the integral from 0 to h of Vx dy. So what needs to happen here is you're going to just plug this in right over here. I'm going to plug it in right there and solve for Q. So you'll know Q then, and it should work itself out pretty well. You'll have, so in your answer, you need to have Q is an expression. And what you'll find is that it will be an expression with V0 in it. And the question above asks for estimate of V0 based on the known parameter H and Q. And what you'll find is you can easily solve for also V0 equals something. You'll have something, and then you'll have Q. So just keep that in mind. So this is what you should do for our homework question number 2. Great, let's move on to the next question. Great, let's start with question number 3. So this question says there's incompressible steady state flow, and the inlet between parallel plates is uniform. So we know that this is going to be uniform. V0 is 8 centimeters per second. And downstream, the flow develops into the parabolic profile. So we're given this as well, this expression, that is for this. And then we also have here, this is helpful, A is a constant. A equals constant. This is the symbol for constant. Now the question is asking, what is the maximum value of Vx? What is Vmax, right? So that's what we're solving for. So in order to find Vmax, let's just take a couple steps. Let's work backwards from this. That means we need to know Vx. And this is in terms of Z. Let's be clear right here. It says right here, this is in the Z direction. The flow profile determines on the position in Z. So Vxz, we need to know, and we are given that expression above, right over here. But as you can see, we have A. We don't know A. So in order to find this, we need to know what is A, right? We need to determine that. And the best way to determine that is to first, as always, we're going to start with the conservation of mass equation statement. Great. So let's start with that. dm dt equals the mass change from the wall, then from the inlet, and then the outlet, right? So as you can see, we don't have anything going in and out from the walls. We can cross that term out. We also know that it is steady state flow. So that is 0. What does that mean? We have 0 equals the mass flow from the inlet minus the outlet. Great. So now what's going to happen is you'll plug both of these values in. We need to solve for what we do know. So let's just recall. Let's recall from our quiz section and also from our lectures. We do know several things. We know, let me just write this out right here. So for the inlet, we do know it is a constant. It's given a uniform flow velocity right over here. So we can use our expression after Q. We have rho times our velocity times the cross-sectional area of flow. So we'll just write cross-sectional area right here for now. So we do know that the cross-sectional area is going to be the height of Z0, which is given right over here. Z0 times what? We're going to use W as an arbitrary width. So we're just going to assume that there's an arbitrary width W. Sorry about that. Let me write this out better. We have an arbitrary width W, and I'll show you why that works. So we will do that. Then let's go on to W out. We know in this case, we can't use this expression because we actually have a profile of flow. It's not a uniform flow. So using an average velocity would be a terrible approximation of this flow, right? So we're going to use the integral. So we have rho, and then we also have the integral. And then that's the integral of Vx, the velocity profile, and then the cross-sectional area in terms of the cross-sectional area. Great. So what's going to happen here is you have the same thing as the previous question. We know dA change is actually, we have the change in the Z direction times the width, because again, the width doesn't matter, but the Z direction, actually you have a different flow velocity profile, as you can see, as you move along the Z. So we know the Z is changing, so let's rewrite that. So we have rho, and then again, 0 to Z0, right? We have 0 right here, and then we have Z0 right here. Great. So 0 to Z0, we have Vx, which you're going to plug in Vx right over here. Vx right over here, you're going to plug that in right here. Then you also have dz, as we found right here, times width. And you're going to pull out that width as well. So when we move everything back into this expression right here that we wrote for the conservation of mass, you'll see. Minus rho. We can pull out that width again. Z0 Vx dz. Great, and you'll notice right away that several terms do cancel. If we pull this over to the other side, we know sorry about that. 0 to z0 Vx dz. Then we're going to write rho v0 z0 times width. And right away, rho cancels, width cancels. So in the end, we're left with this expression, which when you actually do take the integral of this, you will be able to solve for A, right? That's because you're going to be plugging in your expression of right here, Vx equals AZ, Z0 minus Z. Right? And an easy way is to distribute this out and then take the integral. And you'll end up with Z0 terms, and you'll have an A terms, and you'll basically find that A value that allows us to actually continue on. So once we know A, then we know Vx. You can just plug in that A right back into Vx. Then now let's talk about Vmax. So what is Vmax? Let me add a new page. What is Vmax? So I know before we've been kind of saying that it is in the center of the flow profile of the flow. And also we can double check that in this way, because you might also have a flow profile. It's maybe like this, right? You could have other flow profiles like that. So let's start thinking of this in a different way. We know then if we take the derivative of the flow profile, that will be when the slope is 0, right? That means when the slope is 0, it is actually at its maximum. So we know this from calculus, right? So let's actually, we're going to see Vx right here. Great. Now let's actually take the derivative. We're taking it with respect to z, right? So we have az0. I'm going to actually distribute these out. az0 minus 2az. Then we need to set it equal to 0 because this slope right here is 0. dvx dz equals 0 at this point, right? Let's keep working. So we know this. Now easily, we're just going to solve for z, because this will give us the z position where that slope is 0. So solve for z. Solve for z, and that gives you the position where at the z that you find, that is where dvx dz is equal to 0, and that is where Vmax is found. So once you find that z, you're going to plug this z value back into your final Vx equation after you solve for A, right? You'll actually have A, and I'll denote that by drawing a little star here. You'll know what A is. So make sure you find A first, then you're going to plug in Z, and then that is equal to Vmax. So ultimately, you'll have Vmax equals boom. And what I really recommend in this question is just keep that V0 as V0, keep it at V0, keep that VO in there until the very end, and then plug it in. V0, as a reminder, is 8 centimeters per second. So then you're going to plug it in at the very end, boom, times 8 centimeters a second, then you'll have a maximum velocity expression in the units of centimeters per second. Great, and that is what you want to be finding. Great, let's move on to the last question. All right, we made it to question 4. So we have a hypodermic needle containing a serum, and if the serum is to be injected steadily at 6 centimeters cubed per second, how fast should the plunger be advanced? And we have 2 scenarios here. If we have leakage is neglected, what is leakage? Well, leakage is simply any mass from the wall, right? Mass change due to the wall. And then we have a second scenario if leakage is 10% of the needle flow. So we have those 2 scenarios. So we need 2 different answers. Now we also have injected steadily at 6 centimeters cubed per second. Well, that's great. So if it's injected, that means we know the overall flow. The overall flow, actually, sorry, let's use our black ink right here. Our overall flow, that means, is 6 centimeters cubed per second. So we do know our flow. What else do we know? Well, we also know these distances right here. This is 2 centimeters, and this is 0.8 millimeters, right? So we know our flow, and it's asking us about how fast should the plunger be advanced. That means it's asking, what is V? What is V? Right, so we need to find V. We know how much fluid is actually leaving this needle. That means let's write out our expression for Q. So we know our expression for Q is going to be, in this case, it's injected steadily right here, as we can see right here. So we can just use our average velocity. So let's write that out. We have our rho, then we have our V that we're trying to find above. Then we also have times cross-sectional area. Well, what is our cross-sectional area? Luckily, we know that our needle syringes are in cylinders. So great, it's just pi r squared. And one thing to note is r is not equal to 2 centimeters. It is not. It is actually equal to 1 centimeter. 2 centimeters is the diameter. So please keep that in mind. And from here, we want to also just check our units. We want to make sure as we keep going, cross-sectional area is pi 1 centimeter squared. Pi centimeters cubed or squared, right? So great. We know this. We also know rho, which is 1. We have this right here. Well, that means we have Q equals V pi centimeters squared. Well, what else do we know? Well, now we can simply put this in right for Q, be very mindful of units, and then solve for V. That's all. And since it's velocity, we'll know it'll be in centimeters per second. Great, so this would be for part A. So for part B, we know that leakage is 10% of the needle flow. Well, what's flow? Flow is simply 6 centimeters cubed per second. So what's 10%? 10% is essentially 0.6. So if we have this much leakage, if we have this much on the normal flow, that means our total flow is going to be 6 plus the leakage. Great. And then now we have our new value of Q. And we need to go through this exact same process that we did above to ultimately find V equals blank cm per second. Great. So this is the end of question number 4. And another TA will actually be working on questions 5 through 8. And we'll be uploading that video shortly. If you have any questions on any of these questions or also through 5 through 8, we will be having office hours on Monday in person, as well as my Zoom office hours available from 5 to 6 p.m. And we always use that same section AB link. So if you have any other questions, please come. Always here to help. I know this homework is a bit longer, so try to get it done as soon as you can and bring all the questions you have. We will also be working on questions 5 through 8 during quiz section on Monday. So just look forward to that. Hope you have a great rest of your day and see you soon.